Hello students, in today's lecture we are going to learn about waves. In this lecture we will cover NCERT section 14.3.2 to 14.3.3. We will also solve an example 14.2. This is our disclaimer. Learning objectives. By the end of this lecture you will be able to understand key wave parameters, wavelength, angular wave number, period and angular frequency. The topics we are going to learn in this lecture are: first, 14.3.2 wavelength and angular wave number, then 14.3.3 period, angular frequency and frequency, and last we will also cover uh, an example 14.2. Let's start by looking at the concept of wavelength in waves. Wavelength is a fundamental property of all type of waves, whether we are talking about sound, light or water waves. Now let's define wavelength more precisely. So we can say the wavelength is the minimum distance between 2 points on a wave that are in the same phase. That means these points are doing the same thing at the same time, like both being at the top of a crust or the bottom of a trough. To make this clear, we can choose points that are both crusts or both troughs, since these are easy to spot and are always in the same phase. So the wavelength is simply the distance between two consecutive crusts or two consecutive troughs. So take a look at the figure wavelength of a progressive wave. The distance from one crust to the next is the wavelength. One crust to next one is the wavelength. This is true for all type of waves, whether they are on water, sound waves, in air or light waves. Alright. We use the Greek letter lambda, written as this one, lambda, to represent wavelength. Or we can say the distance between trough, one trough to another is also wavelength. Its SI unit is meter, represented by small m. I hope this is clear. Now let's understand wavelength mathematically. We have wave equation as y of xt is equal to a sine kx minus omega t plus phi. In this formula, y is the displacement at position x and time t. Small a is the amplitude, the maximum displacement, and small k is the wave number, 2 pi divided by wavelength. Omega is the angular frequency, 2 pi into f, and phi is the initial phase. Alright. If we set the initial phase phi to 0 and look at the wave at time t equal to 0, the equation simplifies to y of x0 is equal to a sine kx. This means we are just looking at the shape of the wave along the x-axis at a single instant. Now, uh, the sine function repeats its value after every 2 pi. This means that if you move along the x-axis, by a distance that corresponds to 2 pi in the function's argument, the sine wave starts its pattern over again. Take a look at the figure, sine wave representing its pattern after 2 pi. Alright, so the wave looks exactly the same after each 2 pi. So 0 to 2 pi, then again it repeats pi, 2 pi to 3 pi, then so on. Alright, exactly the same after each 2 pi interval. Mathematically, we can write this repetition as sine kx is equal to sine kx plus 2n pi, where n is any whole number. Here k is called the wave number and it tells us how many wave cycles fit into a certain distance. This equation shows that the sine function and therefore the wave repeats itself whenever the argument increases by 2n pi. Let's rearrange that equation to focus on the position x. So we get sine kx is equal to sine k into x plus 2n pi divided by k. And this tells us that if we move a distance of 2n pi divided by k along the x-axis, the wave repeats itself. That distance is the wavelength. Clear? Now, let's understand the relationship between wavelength and angular wave number in waves. So, we got sine kx is equal to sine k x plus 2n pi divided by k. Here k is called the angular wave number and x is the position along the wave. This equation shows that the sine function repeats itself after a certain distance. So from the equation y of x0 is equal to a sine kx, we see that the displacement of the wave at position x depends on the sine of k times x. Alright. So displacement is the same at position x and at x plus 2n pi divided by k. This means that if you move a certain distance along the x-axis, the wave returns to the same value. Here n is any positive integer 1, 2, 3 and so on. To find the least distance between points with the same displacement, we set n is equal to 1. This gives us the shortest possible distance where the wave pattern repeats itself. By substituting n is equal to 1, we get lambda is equal to 2 pi divided by k. Here lambda is the wavelength measured in meters and k is the angular wave number in radians per meter. This formula shows that as the wave number increases, the wavelength gets shorter. Alternatively, we can rearrange the formula to get k is equal to 2 pi divided by lambda. Alright. Remember, this relationship helps us switch between describing a wave by its wavelength or by its angular wave number, depending on what information we have. Let's continue our discussion on wavelength. Here we introduce the angular wave number, also known as the propagation constant, represented by k. The formula is k is equal to 2 pi by lambda. where lambda is the wavelength. This means that as the wavelength gets shorter, the wave number increases. Its SI unit is radian per meter. Alright. Now let's understand angular frequency. Angular frequency tells us how quickly sometimes oscillates or vibrates. So let's look at the figure 14.7. 14.7. This graph shows how a single point or element on a string moves up and down as a wave passes through it. The amplitude, small a, which is the maximum distance the point moves from its rest position, and the period is t, which is the time it takes to complete one full cycle. Now let's examine the general equation for the displacement of a wave. Y of xt is equal to a sine kx minus omega t plus phi. Here y is the displacement at position x and time t, and small a is the amplitude in meters. Alright. So changing a makes the wave taller or shorter, while changing omega makes the waves oscillate faster or slower. So if we focus on a fixed point, say x is equal to 0, and set the phase constant phi to 0, the equation simplifies to y of 0t is equal to a sine k0 minus omega t plus 0. This means the displacement at that point depends on time and the angular frequency. Now, rearranging the terms, so y of 0t is equal to a sine minus omega t. So it will be y of 0t is equal to minus a sine omega t. This just flips the direction of the wave at x is equal to 0, but the frequency and amplitude stay the same. Now let's focus on a key property of the sine function. So it's this property is very important. So it repeats itself every 2 pi radians. Every 2 pi radians. Alright. That means after an increase of 2 pi radians in the angle, the sine value returns to where it started. You can see in the figure sine wave repeating its pattern after 2 pi. That the sine wave pattern repeats after 2 pi. Alright. So for one complete cycle, the argument of the sine function must increase by 2 pi. That means omega times the time period t equals 2 pi, or we can say omega t is equal to 2 pi. This relationship helps us connect angular frequency to the period of the wave. Now, by rearranging omega equal to 2 pi divided by t. Alright. So omega or we can say angular frequency tells us how many radians the wave covers per second. It's called angular frequency because it measures how quickly the phase of the wave changes in terms of angles. The SI unit for angular frequency is radian per second, written as RAD, radian and per second. This means we are measuring how many radians the wave completes in 1 second. Now let's discuss frequency, which is a fundamental concept in the study of waves. First, let's define frequency. Frequency is the number of oscillations or cycles that occur every second. For example, if a pendulum swings back and forth 10 times in 1 second, so its frequency is 10 per second. All right. Now let's look at the formula for frequency. Nu equal to 1 upon t. Frequency, which is we usually write as a Greek letter nu, is equal to 1 divided by time period t. So we have the formula for frequency. This means that if the time period for one oscillation is short, the frequency will be high and vice versa. So since t equal to 2 pi upon omega, the time period t can also written as t equal to 2 pi divided by omega, where omega is the angular frequency. So if we substitute t equal to 2 pi divided by omega into our earlier formula, we get nu equal to omega upon 2 pi. Alright, this is a very useful equation, specifically in physics problems involving circular motion or waves. Its SI unit is radian per second, commonly used in hertz, SZ. Now, in other words, frequency is the number of complete wave cycles that pass a point in a given amount of time. So, the diagram that is given helps us to understand the low frequency and high frequency. Clear? So, look at figure, frequency of wave. Number of cycles here. Many cycles are present in the same length of time or space. So, first, low frequency. Low frequency waves are characterized by fewer wave cycles within the same time frame. Same time frame, but lower wave cycles. This one, number of cycle is less as compared to high frequency, resulting in a more spread out appearance. Resulting in a more spread out appearance. All right. So, whereas high frequency wave exhibit more wave cycles. More wave cycles. This one. Look at here. High frequency. In the figure, you can see that the waves are packed closer together with more cycles in the same space. So, low frequency waves are spread out and have fewer cycles, while high frequency waves are compressed and have more cycles in the same time frame. I hope this is clear. Now, let's see displacement wave equation for longitudinal wave. So, in the discussion till now in this chapter, our transfer waves is considered y of x t is equal to a sine kx minus omega t plus phi. For a longitudinal wave, in a longitudinal wave, the displacement of each element of the medium is parallel to the direction in which the wave moves. This is different from transverse wave, where the displacement is perpendicular. So, displacement of an element of the medium is parallel to the direction of wave propagation of the wave. So here, look at here, figure longitudinal wave motion and particle motion. Alright, both are parallel. Yes or no? So, particles move back and forth in the same direction as the wave travels. This is a key feature of longitudinal wave, like sound waves in air. Now, let's look at the displacement equation for a longitudinal wave. The formula S of x t is equal to a sine kx minus omega t plus phi. Alright. So, S of x t is the displacement of the medium element at position x and time t. In a sound wave, for example, S of xt tells us how far a tiny bit of air has moved from its normal position at a certain place and time. So other quantities are the same as for our transverse wave with the displacement function y of xt replaced by x of xt. The main difference is that we use x of t for longitudinal waves instead of y of xt for transverse waves. Example 14.2. A wave traveling along a string is described by y of xt is equal to 0.005 sine 80.0x minus 3.0 t, in which the numerical constants are in SI units: 0.005 meter, 80.0 radian per meter, and 3.0 radian per second. Calculate A. The amplitude, B. The wavelength, and C. The period and frequency of the wave. Also calculate the displacement y of the wave at a distance x is equal to 30.0 centimeter and time t equal to 20 seconds. Alright, let's see the solution. First, let's recall the general equation for a traveling wave. Y of xt is equal to a sine kx minus omega t. Given equation is y of xt is equal to 0.005 sine 80.0 x minus 3.0 t. So by comparing equations term by term, so amplitude A is equal to 0.005 meter. Wave number k equal to 80.0 radian per meter. Angular frequency omega equal to 3.0 radian per second. Alright. Now, first let's focus on a part A, which asks us to find the amplitude. The amplitude is the maximum displacement from the rest position, and it's a measure of how tall the wave is. So by comparing displacement equation of wave y of xt is equal to a sine kx minus omega t with the given equation y of xt is equal to 0.005 sine 80.0 x minus 3.0 t. So amplitude is a equal to 0.005 meter. Alright. Now let's focus on part B of the question. We ask us to find the wavelength. Remember, the wavelength is the distance between two consecutive points that are in phase, like crust to crust or trough to trough. The formula for wavelength is lambda equal to 2 pi by k, where k is the wave number. The wave number k tells us how many radians the wave oscillates per meter, and it's measured in radian per meter. So now let's substitute the value of k from our wave equation. Here lambda equal to 2 pi divided by 80.0. As we know, k equal to 80.0 radian per meter. So simplifying further, 2 pi divided by 80. So solving this, you will be get pi divided by 40. So let's calculate the numerical value. So pi divided by 40 is approximately 0.078 meters. So the wavelength of this wave is about 7.8 centimeters. Clear? Now let's focus on part C of this question, which asks us to find the wave, find the period and frequency of the wave. Remember, the period is the time it takes for one complete cycle of the wave to pass a point, and the frequency is how many cycles occur per second. The formula for the period t is t equal to 2 pi divided by omega, where omega is the angular frequency of the wave. In this equation, omega is the number in front of t in the sine function and it's measured in radians per second. So plugging in the values, we get t equal to 2 pi divided by 3.0. So we know as omega equal to 3 radian per second. So calculating this, we find that the period t approximately 2.09 seconds. This means it takes just over 2 seconds for the wave to complete one full cycle at any given point. All right. Now, frequency nu equal to 1 upon t. So, or we can say nu equal to omega upon 2 pi. This is the second formula. So, nu equal to 3.0 divided by 2 pi. Solving this, you will be get nu equal to 0.477 hertz. This means the wave completes about 0.477 cycles every second. Clear? Now, displacement calculation. The displacement equation is y of xt is equal to 0.005 sine 80.0x minus 3.0 t. Here y is the displacement. Substituting the given values into the equation, we have x is equal to 30.0 centimeter. So we need to convert to meters. So it will be 0.3 meter and t equal to 20 second. So y of 0.3 or 0.320 is equal to 0.005 sine 80.0 into 0.3 minus 3.0 into 20. So calculating inside the sine function, so it will be y equal to 0.005 sine 24 minus 60. Solving this, you will be get y equal to 0.005 sine minus 36. Now, solving for displacement y equal to minus 0.005 sine 36. So sine x is equal to sine x plus 2n pi. So sine 36 radian is equal to sine 36 plus 12 pi. So it will be sine 36 radian is equal to sine 36 plus 37.7. So calculating this, you will be get sine 36 radian is equal to 0.9598. Clear? Now, solving for displacement y. So y equal to minus 0.005 sine 36. So just put the value. So you will be get y equal to 0.005 into 0.9598. So y equal to 0.00479 meter. This is the displacement of the string at x is equal to 30.0 centimeter and t equal to 20 second. This is the displacement is approximately 0.0048 meter. Now let's summarize what we have learned in this lecture. We started by defining wavelength. The wavelength lambda is defined as the minimum distance between two points having the same phase in a wave. Wavelength lambda is related to the angular wave number k by k equal to 2 pi divided by lambda. For a transverse wave, the displacement equation is given by y of xt is equal to a sine kx minus omega t plus phi. For a longitudinal wave, it's s of xt is equal to a sine kx minus omega t plus phi. And period t is related to angular frequency omega by omega equal to 2 pi by t. Frequency nu is related to the period by nu equal to 1 upon t is equal to omega upon 2 pi. In transverse waves, displacement is perpendicular to the direction of wave propagation. In longitudinal waves, displacement is parallel to the direction of wave propagation. The sine function in the wave equation repeats after every 2 pi change in angle. This change helps in deriving relationships between wavelength, period, and their related quantities. Now we have some practice questions. First, a wave has a wavelength of 2 meter. Calculate its angular wave number. A wave completes 5 oscillations in 10 seconds. Find its period t, frequency nu, angular frequency omega. A transverse wave is represented by the equation phi of xt is equal to 0.03 sine 2 pi x minus 4 pi t, where x is in meters and t in seconds. Find its wavelength and frequency. If a wave has an angular frequency of 4 pi radian per second, what is its frequency and period? The displacement equation of a wave is y of xt is equal to 0.02 sine 0.5 pi x minus 2 pi t. Find its angular wave number, angular frequency. Thank you for your attention. I hope this lesson was helpful.